This is Knowing the Universe, the History and Philosophy of Astronomy. I'm Professor Impey, Distinguished Professor in the Department of Astronomy at the University of Arizona. In this module, we'll be talking about the theories of relativity, special relativity and general relativity. And of course, the work of Albert Einstein, perhaps the most famous scientist of the 20th century. Einstein was born in 1879, and he lived through a tumultuous period in physics when there was upheaval in almost every idea from the classical era. People were deciding about the behavior of light, the behavior of the atom, and even the role of physics in society. He contributed to the most fundamental paradigm shift in the history of physics, involving relativistic motion and the quantum theory. Both of these had profound effects on the thinking of astronomical work. In particular, the ideas of atomic structure, how to interpret the spectra of astronomical objects, nuclear physics and how the stars work to produce heavy elements, and cosmology, the evolution of our universe and curved space-time, also the existence of compact objects like black holes and neutron stars. He was an important and influential philosopher of science, too, because thinking like a philosopher was at the core of his thinking about physics. He is perhaps the most important practitioner of the thought experiment, or the imaginary experiment to test an idea. Physics at the turn of the 20th century was redefining the way we think of reality. Space-time and quantum mechanics are fundamental and profound departures from common sense, or what we might call sensory reality. How do we make sense philosophically of this strangeness? We still haven't completely done so, even a century after Einstein's major work. For example, we perceive space and time very differently. So is the four-dimensional space-time construct of Einstein the way the world really is? Common sense says the collection of prejudices acquired by the universe by the age 18. That was Einstein's view. But he also said God does not play dice with the universe. Something about his work and his persona fired the public imagination. He was essentially the scientist, the first truly public, famous scientist in the world. There's a famous incident where he met Charlie Chaplin, both at the height of their power and careers in completely different fields. Einstein said to Chaplin, "What I admire most about your art is its universality. You do not say a word, and yet the world understands you." In return, at a Hollywood premiere of a movie, Chaplin said to Einstein, "But your fame is even greater. The world admires you when nobody understands you." Einstein was influential in politics. He famously wrote a letter to Franklin Roosevelt urging against the use of the atomic bomb, and he was a leading pacifist during the Second World War. In his early life was uneventful. Einstein was born in Ulm, west of Munich, in 1879, into a Jewish family that were not practicing their religion routinely. His father was an electrical engineer and businessman. He moved to Milan to open a new company, but Albert remained in school in Munich. He was an unhappy, rebellious school child. He learned math on his own for the most part. He read philosophy in his spare time. He had a friend, Marcel Grossman, and famously they used to hang out by the banks of the river that passed through the town they lived. He mused once to Marcel Grossman, "What would the world look like if I rode on a beam of light?" It's the kind of fanciful thought a 17-year-old might have, but in Einstein's mind it impelled him towards the theory of relativity. At the age of 16, he failed the entrance exam to the Swiss Federal Polytechnic. He did pretty well in the math and physics part, though. Why did he try early? He was also not happy in school and seemed to be anxious to get to a different teaching situation. So he entered the gymnasium, the high school, in Aarau, Switzerland, to finish his high school. At 17, he renounced his German citizenship to avoid conscription, and he got a math and physics teaching diploma, enrolling at the Swiss Federal Institute of Technology in Zurich. Even there, he had his problems with teachers. He was too independent. He graduated in 1900 and had difficulty in finding any teaching position. He then acquired Swiss citizenship and was not conscripted into the army due to his ill health. Now, contrary to urban legend, Einstein didn't fail math and he wasn't a terrible student. Here's a copy of his report card from high school. But his Munich schoolmaster did write, he will never amount to anything. A pretty famous damning and wrong judgment of a brilliant scientist. In 1902, the father of his friend Marcel Grossmann found Einstein a job at the Swiss Federal Patent Office in Bern. It was fairly simple work for Einstein, given his intellect, but it did occupy him. In fact, much of his work involved electrical signals transmission, which was a new technology at the time, and synchronizing clocks at remote locations. This turns out to be closely related to the issues that you have to deal with in special relativity. His friend Marcel Grossmann was a mathematician working in differential geometry, and that's the math that Einstein used in general relativity. He remained at the patent office for 7 years. During this time, he married his fellow physics student, Mileva Mitrich. It was an unhappy marriage, but they had 3 children. In 1902, he founded the Olympia Academy with friends as a club to talk about science and philosophy, and he continued to read extensively in philosophy. In 1905, he completed his dissertation, A New Determination of Molecular Dimensions. Now he starts his rise to stardom. Like Isaac Newton, and at a very similar age, early in life Einstein had his annus mirabilis, his miracle year. It was the year 1905. He published 4 groundbreaking papers, any one of which would have made the reputation of a physicist at the time. The first on the photoelectric effect, the second on Brownian motion, or how molecules move, the third on special relativity, and the fourth outlining the famous mass-energy relation E equals mc squared. In the aftermath of this brilliant year of work, where in isolation, he still was not a formal academic at the time, so he was out of the mainstream of academia. He still became an academic celebrity. He was made a professor at Zurich in 1909 and then in Prague in 1911. In 1912, he returned to a professorship at Zurich, his alma mater, and a more prestigious university. Max Planck, one of the most influential physicists of the day, immediately recognized the importance of relativity, showing soon the relativistic form of the classical action moved forward into Einstein's theory. Planck's imprimatur probably advanced the theory's acceptance because Einstein was not well known in physics circles. But Planck was less persuaded by Einstein's idea that light was quantized. At the first Solvay conference in 1911, Einstein was able to convince Planck by citing the advantages of quantizing light in thermodynamics. The two became close friends, and Planck offered Einstein a directorship of a new physics institute. It was a very attractive position for Einstein because it had no teaching. Einstein didn't like teaching throughout his life, and he almost never had students. The mass-energy equivalence comes from a short paper which recognizes the implication of his previous work on relativity. No expression is given, but there's a sentence: if a body gives off the energy L in the form of radiation, its mass diminishes by L divided by V squared. In other words, mass and energy are fundamentally the same thing. Einstein wrote a mass m is equivalent, as regards inertia, to a quantity of energy mc squared. It appears far more natural to consider every inertial mass as a store of energy. This is a profound formula. We have to think of mass now as a frozen form of energy, locking up an enormous amount of energy, because in the equation E equals mc squared, c is a large number, the speed of light, 300,000 kilometers per second. Square that and it's a huge number. So you multiply a tiny mass by a huge number to get the amount of equivalent energy. This is a devastating insight into the release of radiation. It's also behind the awesome and fearsome power of atomic energy. The equation was proven experimentally in 1932 by Cockcroft and Walton in a lab experiment. His next work was the photoelectric effect. In 1901, Max Planck had proposed that light could only be emitted in quanta, or discrete packets. This was a way of avoiding what was called the ultraviolet catastrophe, where when calculating all the energy that might come from a radiation situation, all the energy seemed to pile up in short wavelength modes in an infinite amount, which seemed nonsensical in the calculation. In 1902, Philip Leonard found that electrons ejected from a metal in the photoelectric effect had kinetic energies proportional to the frequency of light but not its intensity. It bothered Einstein that matter as composed of particles was described by a finite number of quantities, while electromagnetic fields were described as a continuum. So he speculated that the energy of light should be distributed discontinuously in space. Einstein showed that the equilibrium distribution of energy in the radiation field behaved like a collection of quantized energy, or energy quanta. If this were so, it would explain the wavelength threshold seen in the photoelectric effect, where red or low energy light does not release electrons from the metal regardless of the intensity of the radiation. Bombard it with more and more red light and nothing ever happens. No electrons are released. But higher energy, green or blue light, kicks out electrons with energy to spare, even at low intensity. This phenomenon of photoelectric effect only makes sense if photons are like tiny packets of energy, or bullets, where the energy is proportional to the frequency, or inversely proportional to the wavelength. The word photon would eventually be coined in 1925. Einstein's idea of the photoelectric effect and the quantized nature of light in photons was confirmed in 1915 by Robert Millikan. This is the beginning of thinking of waves and particles as versions of the same thing. It was somewhat controversial until Compton showed that light quanta could carry momentum as well as energy. But this pivotal work won Einstein the Nobel Prize in Physics in 1921, not for his more famous work on relativity. And we see Einstein in the popular culture, a famous figure. Offered the presidency of Israel, he declined. Recognized by the man on the street, the only scientist whose iconic face would be on t-shirts or billboards, and eventually, when there was television and radio, in advertising.